Hello, my name is Tino Ebbers. I'm a professor in cardiovascular imaging at Linköping University, and I will talk today about AI in diagnostic imaging of the beating heart. So if you think about imaging of the beating heart, there are many different techniques we can use, and nowadays we get really nice anatomical images, so we can really see the whole structure of the heart. For instance, using computed tomography, ultrasound, magnetic resonance. But lately we also more and more use functional imaging, so we image function, so that can be blood flow, the contraction of the heart muscle, that kind of stuff, because that's very important for the assessment of cardiovascular diseases of the heart and the vessels. One technique that we have pioneered here in Linköping is 4D flow MRI. In 4D flow MRI, we measure the velocity field in the whole thorax over the cardiac cycle, over the beat, so the whole beating heart. And when we do this in the whole thorax, we can afterwards we can analyze this data. We can visualize it in different ways, better understand it, but maybe even more important, we can at different locations compare the blood flow and see where the blood is coming, where it's going. This technique is now used all over the world, both for research applications and clinical applications. So in the clinic, probably the main application is congenital heart diseases. These are diseases which you already have at birth. So while you have a normal heart, you have a left side and a right side, and they're more or less behaving in the same way, blood's coming in and coming out. So in congenital heart diseases, we can have many different things that are happening, but the most common is that you have an opening between the left side and the right side. So the oxygenated blood and the deoxygenated blood, they start mixing, which is not a good way. But these diseases can also be much more complex, so you can have different connections, vessels, even vessels that are swapped. So this is a serious condition, and especially very complex condition, because every patient is different in some way. There are many flavors of it. So you need a lot of investigations, and that is 4D flow MRI is really helpful, because we can really investigate every little bit of the blood flow. We can see if it's going from back or forth, and especially also if we find something that is suspicious or strange, even though the patient is already at home, we can still continue analyzing. So that's used there a lot. But there are quite some limitations as well with 4D flow MRI. So for instance, it's a long measurement time, typically 10 to 15 minutes. Depends a bit on the resolution of the data. So, but it's a balance. The better the resolution, the longer the imaging time. Another one is the reconstruction time. So what you do is you measure in the frequency domain. So you measure frequencies. And then afterwards you do some processing steps which involve, amongst others, that you go to the imaging domain, so the domain you see around you. And this is, because these data sets are very large, this can take 2 to 10 minutes. It's not a lot, but if you want to do this while the patient is still in the magnetic resonance camera, in the system, then it's a long wait. It's an expensive wait as well. And the last one is maybe even the most important one. It's a very complex data analysis. It looks very nice, these images, but it's quite time consuming to do this analysis, because you don't have a real segmentation, as we call it. You don't know what is blood or what is some other tissue. You just get velocities everywhere. So right now there is research going on to solve all these problems. Some of them already used in the clinic, others not. And AI is there a really important technique to be used. For instance, recently there has been a study from Zurich in which they showed that they can use AI to decrease the reconstruction time by just replacing the conventional techniques with AI. They could reduce it from 2 to 10 minutes to seconds, which is definitely a good thing. But we can also use it in other ways. For instance, the segmentation, which I talked to you about. So here I have an example from my group. in which we use it on the carotid arteries, the arteries that supply the brain with blood. So if you get those are pretty prone to plaque, and if this plaque ruptures, you can get a stroke. So it's important that you understand that this is well understood and investigated. Important factors in this case are the plaque composition and the flow dynamics. So MRI is a good technique to investigate this. But we need to have a nice segmentation of the vessels to be able to study the wall and to study the blood flow. If you do this manually, that takes 20 to 30 minutes because they're pretty complex, as you see on this image. But using AI, we can do this in 2 to 3 minutes, and it's completely automatic. So in this case, we got a multi-class segmentation, so we get different parts of the vessels separately, and we used a trained support vector machine network. What we did in this case is we used a contrast-enhanced MRI, so a separate acquisition to do the segmentation on. In this case, what you do is you inject a contrast agent, and then when this bolus passes the heart, you do a really fast acquisition to get really nice images with a lot of contrast, so you really see the blood pool. The disadvantage is you cannot see the beating heart in these images. Another disadvantage is that you need to inject a contrast agent, which is gives an extra cost and is potentially harmful, even though there are very few incidents. But you get an image that it's not moving. Well, the heart, of course, and also the larger vessels, they're moving over the cardiac cycle. So you would like to have that as well. What you can do is you use the anatomical information that you acquire already in this 4D flow MRI acquisition. So you don't you don't measure only velocity, you also measure some anatomical information. But as you see here, it's pretty difficult to even recognize the heart, and especially the different parts of the heart. What you can do is you inject again a contrast agent just before this or under. Then you get a better contrast. So here you can suddenly recognize the left ventricle and the right ventricle, the different parts of the heart, which is helpful. But still, you would like to avoid using this contrast agent at all, because it is expensive and it is potentially harmful. So what we tried here instead is when we have data, when we have the 4D flow data acquired without contrast agent, if we can simulate, we can generate images which has this contrast anyway, as if you would have if you have had used the contrast injection. So we use the cycle GAN for this one, and then you see that you suddenly get much better contrast in the images by just using AI. Of course, the images look nice, but you want to evaluate it as well. So what we did is really look, is the contrast better? And in red you see here that you have a much better contrast between blood and surrounding, which we already could appreciate from the images. But it's also very useful because if we use these images now for the segmentation, then we suddenly see that we get a much better quality. We get much better segmentations of these images. In this case, segmentations were done using an atlas-based segmentation. So we do a manual segmentation of a certain amount of data sets, patients, and then we use those to segment the other data sets. But even though this approach is very advanced, and it's definitely very helpful, because before we had to do this manual, and with this approach developed here in Linköping, it suddenly became automatic. But it still takes some computational power, so 20 minutes maybe, something you don't have to do yourself, but still you have to wait. So also here, AI can help speeding this one up and even get better segmentations, which we have shown here, in which we now use these improved images, and we get segmentations of different parts of the heart using a UNet neural network. So now I have improved the images, but now is the question, can we also reduce the measurement time? Because that's still a big problem. And what you can do then is use super resolution residual networks. So what they do is they increase the resolution of images. So what we did is we acquired images of the heart, and then we reduced the resolution afterwards, as if they were acquired within only 25% of the measurement time. So we reduced the resolution with half. And if we then increase the resolution again using a bicubic interpolation, which is a more or less standard approach, then you get high resolution, but you get quite smooth images. And if you look at the left here, you even see there is a mitral valve here, a cardiac valve, which is, you don't see at all anymore. If you look at the right, we see the ground truth, and there the mitral valve in the red square. That one is definitely there, and you see also much better edges at the wall. If we then look at the AI approach in the middle, then we see suddenly the mitral valve appears again, and also the edges are much better, as you can see, using the super resolution residual network. But now the real challenge comes, and that's using this deep learning approach, super resolution on 4D flow MRI. Because then now we have velocity fields. We don't have just grayscale images. And these velocity fields are described by the law of physics, which means they have also to follow the laws of physics when we increase the resolution. We also have the advantage that we can use these laws of physics instead of only have grayscale images. Another challenge is that these data sets are really large. So we have not only 2D images, we have 3-dimensional images. We have them in 3 dimensions, but in every voxel we have a vector, so it has 3 components, or 1 component and a direction. And those we have over time. Because we have these laws of physics, we also have to analyze this data. We cannot analyze this data one slice at a time, because then we don't know if they follow the laws of physics. So this is definitely a challenge. So we need large computers to solve this. Luckily, we have access to good computers here in Linköping from IDA, and hopefully we'll now soon also get a new Vesalius supercomputer that will come to Linköping so that we can try to solve this problem. So if we summarize this, AI and diagnostic imaging, then the things I see which are now already making its way into the clinic or already are in the clinic is that we get shorter examination times, we get reduced reconstruction times, higher image quality, and fast and automatic analysis. So in total, this will lead to better and more cost-effective diagnosis and disease assessment within imaging. If we go back again to my little example there, 4D flow MRI, what does it mean for 4D flow MRI? Of course, all these, but together it will also allow suddenly the use of 4D flow MRI in new applications and other applications where before we said, oh, this is too complex or too difficult or takes too much time. For instance, in the assessment of heart valves, we have, when you become older, the risk increases that one of your valves doesn't open fully or doesn't close completely, which affects the effectiveness of your heart functioning. And the problem is maybe not to diagnose it, to know if it happens, but how important it is for this heart. Is it worth it to do a treatment, to do surgery maybe, and fix this valve? If you do this too early, the patient maybe will suffer due to the operation unnecessary because it doesn't even help that much. If you do it too late, the heart might already be affected quite a lot because it is working in a difficult way. It is already malfunctioning. But this is challenging because we need high resolution. We get small jets, as you see, and we need high resolution at the same time a short scan time. But I think with AI, this is definitely coming now. This is coming soon, which you also have written down in a recent paper in the Nature Review Cardiology. With this, I want to thank you for your attention.